Let's begin our discussion of radicals by examining this pattern. Notice for a number like 25, we can write 25 as 5 squared. We have two equal factors that compose 25. 5, then, is called a square root of 25. 25 could also be written as negative 5 squared. So negative 5 could be called a square root of 25. For negative 64, we can write as negative 4 to the third power, three equal factors, you see, giving us negative 64. Negative 4, then, is a cube root of negative 64. For 81, we can write as 3 to the fourth power. So 3, then, is the fourth root of 81. Well, suppose we want to write a request for a root. We do so by using a radical sign. Now, here's the radical sign. And here's the last situation we had in that pattern. That is, the fourth root of 81. The number under the radical is called the radicand. The nth-ness of the root, the fourth root of 81, that number in this position is called the index of the radical. Now, here the answer would be, well, what would it be? Well, it turns out that it would be 3. We said that there are 3 to the fourth power is 81. So the fourth root of 81 is 3. Then you might say, well, gee, isn't there another one? Isn't it true that negative 3 to the fourth power is also 81? So wouldn't negative 3 be a fourth root of 81? Well, it would be a fourth root of 81, but let's examine that dilemma here. Suppose we're talking about the square root of 25, and we know that 5 squared is 25, but we also know that negative 5, that quantity squared, is also 25. It turns out that the radical implies that we're looking for what's called the principal square root of that radicand. And this answer would be simply 5 and not the negative 5. If another square root is to be requested, it would be requested in this form. You see, here our answer would be the negative 5. Okay, so this is a request for the principal square root of a particular number. Now, consider this situation. Consider the cube root of a negative number. Now, what we are requesting is a number that can be used as a factor that many times to give this number. Is there such a number that can be used as a factor 3 times to give negative 8? Yes, there is. And that number is negative 2. Negative 2 times negative 2 times negative 2 gives negative 8. Now, this is a rather important example because it is commonly thought that we can't apply a radical to a negative number. And that's simply because we're more used to square roots than anything else. The square root of a negative number makes little sense, doesn't it? Because we're looking for a factor that can be used twice to give negative 25. What number times itself is negative 25? Well, there is no such number. So this is an impossibility. This can't be done. All right. Let's review some of the aspects of taking radicals of numbers. If we're taking the square root of 50, now there is no number that can be used as a factor twice to give 50, but 50 has an even, if you will, square root within it. That is, we can factor 50 into 25 times 2. Now notice, we're factoring it this way because 25 is a square. Now numbers that are squares are numbers that have two equal factors within them. 4 is a square, 9 is a square, 16 is a square, and so on. All right, so we can factor this. Since we're taking the square root of 50, we're factoring into a square times a leftover factor. And we can take the square root of each part when we talk about factors under a radical sign. So this is the square root of 25 times the square root of 2, or 5 times the square root of 2. Now, often, both of these steps would not be written. Only one of them would be written. Probably this one, I would think. So you factor into the squares times the leftovers. You understand that you can take the square root of one of these factors separately, or each of them separately. So we simply write 5 the square root of 2. Now, that situation can lead to other situations. That is, the square root of 3 times the square root of 5. If it's true that we can factor and think of the radical applying to each separate factor, then we can work that idea in the opposite direction. That is, if we have the square root of 3 times the square root of 5, then to simplify this matter, we can write it as the square root of 15. These are equivalent forms, and this is a bit simpler than that is. Now, what about this situation? The cube root of a variable cubed. Well, understand what the radical is a request for. We are requesting a factor that can be used that many times to give this number. Well, this number has within it 3 factors of x. So it should make some sense here that the answer is x. What number uses a factor 3 times gives x cubed? Well, x uses a factor 3 times gives x cubed. Now, it may be thought that the generalization of this is that when that number and this one are the same, we always get that variable in this position. And that's not exactly the case, and let's see why. Suppose we're talking about the square root of x squared. It would be commonly thought that this would always be x. Well, that's true in many cases, but it's not true in all cases, and here's why. Suppose we let x take on the value -4. Then the problem looks like this. We would have the square root of x squared, which is the square root of -4 squared, but -4 squared is positive 16, and the square root of 16, you see, the principal square root of 16 is 4, but not -4. X was -4, our answer turned out to be 4. The idea that if under the radical we are squaring or raising to any even exponent, then the number under the radical is going to necessarily be positive. So you see, squaring a negative or squaring a positive gives us a positive number under the radical, and the square root then will end up being a positive number. So to assure ourselves that in this process we get a positive result, we have to put an absolute value symbol about the variable x. Consider this problem. The square root of 48x to the 5th y squared. What we intend to do here is factor the radicand into a square times a leftover, because we can take the square root of the square part and the leftover will remain under the radical sign. Now, let's take it in pieces for each of the factors, you see. 48 can be factored into, well, we're asking ourselves what's the biggest square in 48? Turns out to be 16. So we'll factor 48 into 16 times 3. Now, what about for x to the 5th? What's the biggest square that's in x to the 5th? Well, it turns out that the biggest square in x to the 5th is x to the power, which is the biggest exponent number that 2 will go into. In other words, it's x to the 4th. So we'll factor x to the 5th into x to the 4th times x. Now, why is this a square? Well, let's see. You see, the square root of x to the 4th, what factor times itself, or what number uses a factor twice, will give x to the 4th? Well, it's x squared times x squared. All right. So we can take the square root of x to the 4th, and in general, it's the index into that exponent, you see, and the largest number that will go into it is what we write here. The largest number that this goes into is written right there. All right, what about y squared? Well, y squared itself is a square, so we'll write y squared here along with the squares. Now, we take the square root of each of these factors. The square root of 16, 4. The square root of x to the 4th, x squared. The square root of y squared is y. And left under the radical is 3x. Okay. For this one, the 4th root of 5x all to the 4th power. We can write 5x all to the 4th power as 5 to the 4th times x to the 4th. Now, the 4th root of 5 to the 4th is 5. And the 4th root of x to the 4th is x, well, not exactly. We have to assure ourselves, remember, in this situation, that x itself is, or that our answer is going to be positive. So we'll have to write the absolute value of x. Now the reason we have to do that is because if this x is negative, that negative number raised to the fourth power will be positive, you see, and we're taking the fourth root of that positive number. We have to assure ourselves that the answer is going to be positive. In this one, the cube root of this radicand, well, we're looking to factor into cubes times leftovers. We factor negative 40 into negative 8 times 5 to give the negative 40. Negative 8 is a cube because negative 2 times negative 2 times negative 2 is negative 8. So we have cubes times leftovers. Now, notice how we handle the x to the 7th. We're factoring into cubes times leftovers. The largest exponent number that 3 will go into. 3 goes into 6, so we write x to the 6th. And the other x factor is written out here. Now, the cube root of negative 8, negative 2. The cube root of x to the 6th, that is, what number or what factor times itself gives x to the 6th? Well, or times itself uses a factor 3 times. It would be x squared, because x squared times x squared times x squared gives x to the 6th. All right, and then 5x remains under the radical. Here's a situation involving a radical in a fraction. It turns out that we don't leave a radical sign in the denominator of a fraction. We resolve that problem by a process called rationalizing. And in rationalizing, it's just a manipulation of the fraction. We're not going to change its value. We're going to change its form, though. And to change its form, we'll multiply in the numerator and denominator by the same number. We're multiplying by a form of 1. That is, we're not changing its value, we're changing its form. Multiply by a form of 1 to cause us to take the square root of a square here. The smallest square that 3 goes into is 9, and it goes 3 times. So what we'll do is multiply here by the square root of 3 over the square root of 3. Now notice, in the numerator we have 5, the square root of 3. In the denominator, the square root of 3 times the square root of 3 is the square root of 9. So we can take the square root of 9, and our answer becomes 5 root 3 over 3. We have rationalized the denominator here. Now there is some thinking that we always will multiply by the same radical that we see here. That's not always the case. Here's a good example. Suppose we have 2 over the cube root of 4. Now, 2 over the cube root of 4, if we multiplied by the cube root of 4 over the cube root of 4, in the denominator we would have the cube root of 16. But we can't take the cube root of 16 evenly. You see, 16 is not a cube. What we have to do is ask ourselves the question this way. What's the smallest cube that 4 goes into? Now, what are cubes? We're more familiar with squares than we are cubes. We might list a few of them. Let's see. 1 times 1 times 1 is 1, so 1 is a cube. 2 times 2 times 2 is 8, so 8 is a cube. 3 times 3 times 3 is 27, so 27 is a cube. 4 times 4 times 4 is 64. 5 times 5 times 5, 125. And these are the most familiar cubes. All right. What's the smallest one of these that 4 goes into? Goes into 8, and it goes twice. So we can transform this denominator into the cube root of 8 if we multiply here by the cube root of 2 over the cube root of 2. So in the numerator, we would have 2, the cube root of 2. In the denominator, you see, we have the same index, so we multiply the radicands, and we get the cube root of 8. Now, we have 2, the cube root of 2 over 2. Well, gee, these 2's can cancel. Our answer then becomes the cube root of 2. Here's another situation involving rationalizing. This one is a little different, however. Notice that in the denominator we have a binomial involving a radical. Now, that radical may appear in one or both of these terms in the denominator for us to do what we're about to do. In order to rationalize here, we need to multiply not by a single radical, but by a binomial involving one or two radicals. Here, we'll multiply by 3 minus the square root of 5. Now, that binomial is called the conjugate of this one. It's essentially the same binomial except with a different sign. So it's the same but different. It's very similar, but it's a bit different binomial. What we're doing is we're taking the fraction that we have and we're multiplying in both numerator and denominator by 3 minus the square root of 5. Numerator and denominator. All right. Now, in the numerator, we get 2 times 3, 6. This is by the distributive property. 2 times the negative square root of 5 is minus 2 root 5. In the denominator, now, we're multiplying two binomials. It turns out that the middle term that we would anticipate goes out here. The sum of terms times the difference of the same two terms. 3 times 3 is 9. And the middle term ends up going out. The last term, plus times minus minus, the square root of 5 times the square root of 5 is the square root of 25, which of course is 5. So in the numerator, 6 minus 2 root 5. In the denominator, 9 minus 5 is 4. Now we have a cancellation opportunity here if we go through a factoring process in our numerator. Now what we don't want to do here is say the 6 and the 4 can cancel, that is 2 into 6 and 2 into 4, and then also cancel here. That would be improper. What we need to do is factor this numerator into 2 times 3 minus root 5. You see, we can cancel factors, but we can't cancel individual pieces of binomials. And we'll get into that kind of thing a little bit later. The important thing here was in rationalizing, to multiply by the conjugate in our denominator. We'll take care of the reduction of this at another time, but the important thing was this multiplication by the conjugate. Consider this situation. The square root of 5 can be written in a different form. You know, earlier we talked about exponents as being a method of telling us how many factors of a base that we have. We use this exponential format to talk about multiple factors of a particular number. Well, it turns out that we can also indicate a radical using an exponent, but the exponent turns out to be fractional. The square root of 5 can be written as 5 to the 1/2 power. This exponent has a numerator and denominator. The denominator of a fractional exponent indicates the index of the radical. Right here, the square root of n cubed can be written as n to the 3/2 power. Now, notice that the 3 indicates what we have in the past thought of as a regular exponent, and the 2 indicates the index of the radical. So n to the 3/2 power. Now, let's turn the situation around and take a situation involving a fractional exponent and see how we would deal with that kind of expression. 8 to the 2/3 power. The fractional exponent implies two things. The numerator tells us that we're going to raise this base to that power. We're going to square 8. The denominator of the fractional exponent says we have a radical, and this is the index of that radical. So the implication here is that we have two operations to perform on this base. We have squaring and we have cube rooting. And it turns out that we can do either of those operations first. That is, we could think of the problem like this. We could say, okay, let's do the cube root of 8 squared. Here we have the cube root of 8, that quantity, squared. We're going to take the cube root first here. We're squaring first here. All right, 8 squared, 64. The cube root of 64, 4. In this case, the cube root of 8 is 2, of 2 squared, 4. We get the same result, of course, either way. If there is a choice here, and if we can take the radical on that base first, then it would be wise to do so, because we would, under normal circumstances, we would deal with smaller numbers by doing that, rather than the 64 here. Fractional exponents can help us in simplifying a number of different kinds of problems. Here's one involving a rather complicated looking radical, the 6th root of 27 squared. If we go from the radical form into the fractional exponent form, it's 27 to the 2/6. And then we reduce the 2/6 to 1/3, and this becomes the cube root of 27, which of course is 3. Now this is only one way of working this problem. There are other ways. But it's important to see the kind of manipulation that we can do with radicals using the fractional exponent idea. All right, here's a negative 32 raised to the negative 4/5 power. Now, let's understand what this means. We have a sort of a regular exponent, or we're raising to the negative 4 power here, and we're also taking the 5th root. That's one way to look at it. So let's do what we said earlier, that we have two operations to perform, and if we can, we would like to perform that root first. So let's consider the 5th root of that number. So the 5th root of the negative 32. And whatever we get as a result, we're going to raise to the negative 4 power. All right. So the 5th root of negative 32. What number uses a factor 5 times gives negative 32? It turns out to be negative 2. Now what about negative 2 to the negative 4 power? By the way, these signs here, this negative on the 2 and this negative on the 4, are not related to one another in any way. They're not even distant cousins. This indicates an entirely different kind of thing than this does. This says the base is misplaced. So really this means 1 over the negative 2 to the 4th power. Negative 2 to the 4th is 16. So our answer is 1/16. Here's one of my favorites, a kind where we have a radical within a radical, and it's so simple to do if we just move into the fractional exponent form. The cube root of 25 can be written as 25 to the 1/3 power. Okay, that's one step, just looking at the what's under the square root symbol here. Okay? Now, what does this mean? Well, it means that this radicand, you see, is raised to the 1/2 power because of that radical. The square root implies raising to the 1/2 power. So it's 25 to the 1/3 to the 1/2. Raise a power to a power. What does that mean? Well, it means multiply the exponents. So 1/3 times 1/2 is 1/6. So this is really 25 to the 1/6 power. Well, or we could write it as the 6th root of 25. Now, is this as simple as we can get? Well, no, not really, because 25 has factors within it that are alike. 25 can be written as 5 squared. Now, please notice and understand that this is only one treatment of this problem. The problem could be done effectively in a couple of other ways. At any rate, let's continue the problem. Let's write this as the 6th root of 5 squared. And then going into the fractional exponent form, this is 5 to the 2/6 power. But 2/6 is reducible to 1/3, so it's really the cube root of 5. Turns out that radicals can be collected. Terms involving radicals can be collected if they involve situations like this. Notice the same radical in both terms, the square root of 2. Now, these radicals have to have the same radicand and the same index. But in that situation, it's almost like the radical takes on the same properties as a variable would take on, as though we had 7x minus 4x. The radical is playing the role of the x. 7 of these things minus 4 of these things gives us 3 of this same kind of thing. So when we're trying to simplify situations like this, we'll simplify both parts or both terms in our problem and then just see if we have like terms once we've simplified each of them separately. Here, 48 for 3 to the square root of 48. 48 is 16 times 3. Well, let's continue with this part. The square root of 16 is 4 outside of the radical. 3 times 4 gives us 12. So we have 12 root 3. Now back up to the top, we have 27, which is 9 times 3. The square root of 9 gives 3 outside of the radical. 2 times 3 gives us 6. So we have the minus 6, the square root of 3. Oh, happy day. We have like terms here. You see the same radicand and the same index. 12 of these things minus 6 of the same thing gives us 6, the square root of 3. Here's one more that will work using a calculator. Now, we're talking about taking the cube root of 56, and we can do that on the calculator using the y to the x key. Most calculators that I'm aware of don't have a cube root key. A lot of them have the square root key, but not so much a cube root key. At any rate, we can write this as 56 to the 1/3 power and use the exponent idea, the y to the x key, to get a result. We would input 56, hit the y to the x key, and now it's a request for the exponent. But the exponent involves an operation, 1 divided by 3. So what we would do to indicate the exponent is open a parenthesis, and then we would write 1 divided by 3, and close the parenthesis. And when we close the parenthesis, the calculator is performing 1 divided by 3. All right, then when we hit an equal sign, it'll give us our answer. And this is the approximation of the cube root of 56. This top expression is called a polynomial. Now, the coefficients involved here, as we have seen earlier, would be 3 and -7, 2 and 4. The degree of a term refers to the exponent on a variable. The degree of this term is 4. The degree in this term is 2. The degree in this term is understood to be 1. And actually, the degree in this term can be thought of as 0, because we could write this as 4x to the 0 power, you see. So, the degree refers to the exponent on a variable. Now, notice that in this polynomial, there is no term of the 3rd degree. There's no term that has an exponent of 3 on it. So we could actually, if in some circumstances, you see, it's necessary to rewrite the polynomial so that there is a term of every degree from the highest one on down to 0. So it might be necessary to rewrite the polynomial in this form, so that we'll have distinctly a 4th degree term, a 3rd degree term, a 2nd degree term, a 1st degree term, and a 0 degree term. Now, in that circumstance, the coefficients would be thought of as 3 and 0 and -7 and 2 and 4. Now, usually polynomials are written in the form that this one has been written in, that is, in decreasing degree of our various terms. And notice that since the term of highest degree is written first, that the polynomial itself is said to be of that degree. That is, this is a 4th degree polynomial. The degree of the polynomial is the same as the highest degree of any single term within the polynomial. All right. Now, this is a polynomial in x. This is a polynomial in x and y. Now, notice the coefficients 5, -1. The 1 is understood here. So the coefficient is said to be -1. 2 and -5. The degree here, now we talked about degree as being the exponent on a variable. Well, here it's the sum of exponents on the variables. This is a 4th degree term, 3 and 1, you see. This also is a 4th degree term. This is a 2nd degree term. All right, the degree of the polynomial is 4, because these two terms are 4th degree terms, so a 4th degree polynomial. Well, let's talk about some operations on polynomials, the 4 fundamental operations. Let's begin with adding and subtracting. The adding and subtracting is done by simply showing the various terms involved in both or all of the polynomials involved in the operations of adding and subtracting, and then bringing like terms together. Here's what I'm talking about. Suppose we have this polynomial and we want to subtract that one. Well, all we do is we drop the parenthesis in this way. This is understood to be a 1 preceding this polynomial, and the parenthesis here can be thought to indicate multiplication. So it's like 1 times all the terms in the parenthesis, and we get all those terms back. This can be thought of as -1 times all of these terms, and therefore the -1 times x squared, you see we get the minus x squared, and the -1 times -6 gives us the plus 6. Well, now we're ready to collect like terms. Oh, by the way, this business of changing the signs here when a minus sign precedes the parenthesis, the common error is to change only the sign of this first term in parenthesis and not change the signs of all the other terms. But so it's important to concentrate on that until this situation is familiar. Now, we collect like terms. Like terms are terms that have the same letters and the same exponents involved in them. And to collect them, we simply collect their coefficients. Here, this term and this term are alike. So we collect 4 with -1 and get 3. So we have 3x squared, you see, in collecting those two terms. This term has no other term that's like it, so we simply bring it down. And the constants, of course, are alike. We bring them together to get 8. We can't take this any further, or we can't simplify any further. These are unlike terms. To multiply polynomials, it turns out that fundamentally, we just want to make sure that every term in this polynomial is multiplied times every term in that polynomial. And there are a number of little routines to assure ourselves that that happens. One way to do it is to follow the procedure that might be prescribed in the distributive property. That is, think of this as a single item. Now, this item is multiplied times x plus 3. So we could think of it as this item times x, you see, and this item times 3. And now use the distributive property, you know, from the other direction, and we'd have x times x, x squared, x times 2, 2x, then 3 times x, 3x, 3 times 2, 6. And collecting like terms, we notice that 2x and 3x give us 5x, and the outside terms are brought down. Well, this is just one pattern that can be followed to multiply binomials. Another pattern that it may be a little more familiar to you is the FOIL method, F-O-I-L, standing for the first terms, the outer terms, the inner terms, and the last terms that are involved in the binomials. Now, this pattern works for binomials, and it's designed for binomials that really are of the same degree. At any rate, first means first times first. X times x, x squared. The outer ones, x times 3, 3x. The inner ones would be 2 times x, 2x. And the last ones, 2 times 3, 6. Now notice that the 3x and 2x are brought together to give 5x. Another pattern that works quite well, and I ran into this one when I was in high school. It follows the FOIL method, but it's kind of like this. It's like, okay, we're anticipating a trinomial result for our answer. And we understand that if these two binomials are in standard form, that is, the terms of highest degree appear first, then x times x, this term times this term, will give the term of highest degree in the answer. So x times x gives the x squared. And the last term, or the last ones multiplied, will give the term of lowest degree in the answer. So 2 times 3, 6. And we may anticipate, because it happens so often, that we'll collect this product and this product to get the middle term. So it'll be like 2x and 3x to give 5x for the middle term. So that pattern works as well. But notice that all of the patterns follow the general prescription that every term in one polynomial is multiplied times every term in the other polynomial. And actually, you have to go through that kind of idea of thinking about each term over here is multiplied times each term over there when multiplying binomials times trinomials, or when multiplying two trinomials times one another. Okay, let's continue the process. This is a rather special kind of product. This is the sum of two terms times the difference of the same two terms. And it turns out that the result of this multiplication is rather predictable. Now, notice what happens. It's if we followed the FOIL method, the middle term would actually disappear. The two terms that are combined to give the middle term go out, because it would turn out to be 3x with negative 3x, and they would add out. So what it turns out to be is x times x squared, and then minus, because plus times minus, the square of the last term. So here's how we think about it when we're faced with the sum of terms times the difference of the same two terms. It's simply the first term squared minus the second term squared. You see, and then very quickly we can get x squared minus 9. Now this idea of thinking of first term squared minus second term squared when faced with that situation can help us in a problem like this. Notice we see the sum of terms times the difference of the same two terms. So here's what we think. We may write down the answer directly, but we could write this down. We think first term squared minus, because plus times minus, the second term, pick either one, you see, squared. Now I'm thinking of it, when I say the second term, I'm thinking of it without regard to sign. The second digit is what I probably should say here. But at any rate, it's 5x quantity squared, which is 25x squared, and the 9 squared gives us 81. So 25x squared minus 81. Now, it's important to see the difference between what we just did and this problem, which is x plus 4 squared, a binomial squared. Now, the expansion of this, what this means, is x plus 4 times x plus 4. And if using the FOIL method, we would get x squared plus 4x plus 4x plus 16. And collecting the two 4x's here, we get 8x for the middle term. However, this collection of two terms that are alike to get our middle term is a predictable situation. It will happen every time we're squaring a binomial. These two binomials will be the same, you see. So this product will be exactly like that one. So a faster way to do this would be to say, okay, our answer is going to be composed of the square of the first term plus twice the product of these two terms, see, plus twice 4x, then plus the square of the last term. So very quickly we can come to that same answer, x squared plus 8x plus 16. Here's another binomial for us to square. Now, be careful with squaring binomials. A common mistake is to just square this first term and then plop in a minus sign and square that 3 and have an answer as a binomial. Of course, that's wrong. We know from our pattern that that's not quite right, that we are going to get a middle term here. At any rate, let's see. We've got our pattern says, take the first term, square it, and then multiply 2 times the product of these two. Well, this product, the negative 3 times 4x is negative 12x. And the last term is this item squared. And we can think of this as either negative 3 squared or simply 3 squared, because it's going to be positive in either event, you see. Just make it easy on yourself. Whatever you get used to is fine. The negative 12x times 2 is negative 24x for the middle term. Now, it may seem like since we have a pattern for squaring a binomial, perhaps we have a pattern for cubing a binomial. And we do. There is a pattern for cubing a binomial. It's a little more complicated, though, and not perhaps as easy to remember because it is not used as often. And because of that situation, often it's wise just to understand fundamentally what's going on when we're like cubing a binomial. And that's the way we'll work the problem at the beginning. And then we'll look at the pattern involved. But if the pattern is forgotten, then the fundamental idea of multiplication is what we need to fall back on. All right, here's the fundamental idea of cubing a binomial. We understand we have 3 factors of that binomial. All right, now we understand that multiplying these two would be the same thing as squaring 3x plus 2. So let's go through that squaring process. Let's see. 3x, that term squared is 9x squared. Then 2 times the product of the two terms. Well, this product is 6x. 2 times 6x, 12x. And the last term, when we're squaring the binomial, is the last term squared, which in this case is 4. Now what we've done is we've squared the binomial, which means we've multiplied these two. Let's bring down this other term. Now, multiplying a trinomial times a binomial. Well, all bets are off now on some kind of pattern. We resort to whatever pattern it takes to assure ourselves that every term here is multiplied times every term there. One way to do it is like this. take the first term of this first polynomial and multiply that term times every term over there. It would be 9x squared times 3x, then 9x squared times 2, then 12x times 3x, then 12x times 2, then 4 times 3x, and then 4 times 2. You see, this thing stretches out, doesn't it, quite a bit. Let's simplify a little bit. Let's see what happens when we go through the simplification. Let's go way back over here. The 9x squared times 3x, 27x cubed. 9x squared times 2, 18x squared. 12x times 3x, 36x squared. The thing to note here is that we have two terms of the second degree, two squared terms, you see, that we'll collect in the next step. All right, let's go on. 12x times 2, 24x. 4 times 3x, 12x. Again, like terms here to be collected in the next step. And then the 4 times 2 gives 8. All right, let's come back and collect those terms that were alike. The squared terms collect to give 54x squared. The first degree terms collect to give 36x. And of course, we bring down the 8 and we bring down the 27x cubed. All right, notice here's our polynomial answer. Now let's look at the pattern that can be used to multiply or to cube a binomial. Here's what that pattern is all about. It turns out that in cubing the binomial, the first term of the answer will be this first term cubed. So the first term will be 3x quantity cubed. Now the second term will be 3 times the product of this item squared times that item to the first degree. So 3 times 3x squared times 2. The next item is 3 times this one to the first degree and that one squared. So it's 3 times the first term times the second term squared. So notice the similarity and difference. These two terms both have 3 as a factor in them. And in this one, the first term is squared and the second term is to the first power. And in this one, that one's to the first power and this one is squared. Okay, and the last term in cubing is the last term cubed. All right, let's see what we get here. Well, 3x cubed is 27x cubed. And here we have, let's see, the 3 squared would give 9. 9 times 3, 27. 27 times 2, 54. And the x is squared here, so we get 54x squared. For this one, the 2 squared gives 4. 4 times 3, 12. 12 times 3, 36. And the x is brought down as a factor. So 36x. And then 2 cubed gives 8. Now, notice that in our pattern here, this takes care of the highest degree term, and this product involves everything needed to give us our squared term, and this takes care of everything needed to give our first degree term, and here's our constant term. So everything is laid out for us in this pattern. You know, we've been talking in this section about multiplying and mostly and doing other operations with polynomials. One of the operations, one of the properties that we've used over and over again is the distributive property, and we've talked about it earlier. But the distributive property shows up in many rather unexpected places in mathematics. And it might be worthy of us to just take a moment here, relax, and let's look at a couple of places where the distributive property shows up. In geometry, the distributive property can be seen by examining the area of rectangles. Now, the area of a rectangle is given by the formula area is length times width, or A is equal to LW. Now, consider this rectangular configuration. We have a larger outside rectangle and 2 small inside rectangles. Consider the outside rectangle first. Now, its area is length times width. The length of this rectangle is B plus C, and its width is A. So the area of the big rectangle is B plus C times A. Now it should be clear that the area of the big rectangle is composed of the sum of the areas of the 2 small rectangles. Now look at the area of the rectangle to the left. Its length is B and its width is A. So its area is B times A. Now the small rectangle on the right. Its length is C and its width is A. So its area is C times A.
Now look at what we have. B plus C times A is equal to B times A plus C times A. Using our commutative property for multiplication, we can change each of these products around to show that A times B plus C is equal to A times B plus A times C. Now consider this arithmetic problem. 16 times 1 1/2. Under ordinary circumstances, if we have pencil and paper, we've been told we need to work the problem this way. We think of 16 as 16 over 1, and we change the mixed number 1 1/2 to the improper fraction 3 over 2. Now we see a cancellation between the 2 and the 16. 2 into 2, 1. 2 into 16, 8. And now 8 times 3 is 24. And with 1s in the denominators, our answer is 24. This would be a tough situation to think our way through if we don't have pencil and paper. But notice what happens if we consider the problem a little bit differently. Let's apply our idea about the distributive property here and think about the 1 1/2 as 1 plus 1/2 in parentheses. And this is pretty easy to do in your head. Now distribute the 16 through the parentheses. 16 times 1 is 16, you see, and 16 times 1/2, well, half of 16 is 8. Now, 16 and 8, of course, is 24, and we have thought through the problem and gotten an answer just by a little thought process, and we've used the distributive property.